everything we've been working towards is going to come to fruition today because we're going to start spinning those representative rectangles around axes. Problem with this is, number one, it's complicated. Number two, there are 4 different versions of this. Spin it around the x-axis, spin it around the y-axis, spin it around some other horizontal line, spin it around some other vertical line. It's going to get a little crazy. However, I'm going to go slow. I'm going to talk you through the process, and once you get the process under control, you just have to apply it to every scenario. Okay, so it's not like 4 different scenarios. It's one scenario, 4 different variations. So again, if you can do one, you can do the other ones. Okay, so it's going to create 3-dimensional figures. And I know we talked about this before, that if you take some of the functions we've done already, and we found some areas, we talked about what that would look like if you spin it around an axis. So for instance, in your notes, draw a triangle in quadrant 1, connecting a point on the y-axis to a point on the x-axis. Both positive. Okay. So positive y-axis, pick a point. No. Don't draw the whole triangle, just draw the segment so that you get a triangle that's formed by the x-axis, the y-axis, and that segment you just drew. Perfect. Okay, good. Everybody got it? Now, imagine taking that triangle, you can color that triangle in if you're feeling saucy. Imagine taking that triangle and spinning it around the x-axis. What shape would you get? Nope. Push. It becomes a cone. Very good. Okay. Is everybody seeing that now? When you spin it, the triangle becomes a 3-dimensional figure, and that 3-dimensional is a cone. 3-dimensional figure is a cone. Next to that triangle, draw a semicircle with its diameter on the x-axis. I'll say that again. A semicircle with its diameter on the x-axis. If you spin that thing around the x-axis, what do you get? A sphere. Good. Last one. Draw a rectangle with its longer side on the x-axis. You have to extend your x-axis. Is it okay? If you spin that around the x-axis, what do you end up with? A cylinder. Very good. Okay. That's what we're going to be doing. Not only are we going to be creating, now the good thing is you don't really have to draw the 3-dimensional figures. But you will be doing things like finding the volume of those 3-dimensional figures. So if you go back to the triangle, if you assign distances on the x-axis and the y-axis, you can calculate the area of that triangle, which is great, but not very helpful. What we want to be able to do is calculate the volume of the cone that you get when you spin that thing. We want to calculate the volume of the sphere when you rotate that semicircle. We want to calculate the volume of the cylinder when you spin it. Now, those are the easy examples, and you probably don't need calculus to do that. You're all fairly bright. You found the area of 3-dimensional figures. But then, if you take something like a sine function and move it up from the x-axis and then spin that bad boy around the x-axis, you get this weird shape, and we're going to be calculating the volume of those weird shapes. But it's not as bad as you think it's going to be. What do you want?
Does that shape have a name? I'm curious. I know lots of weird shapes.
Not that what would you like to call it? Earl?
Yeah.
Okay, we'll call it an Earl.
Okay.
So you'll eventually be finding the volume of Earl.
Okay.
Beautiful. Here we go. These are called volumes by revolution. We have 2 main methods which break into 4 different types. We're going to use a disk method, we're going to use a washer method, and then of course, for today, try to do something nice for a stranger. Not a friend, not a family member, just some rando on the street, which could get fairly awkward. But try not to make it creepy.
I'm going to work today. I don't think that's possible.
Where do you work?
I work at a gym. I'm a desk person. People are really mean, and it's pickleball night, which is worse.
Wow. That's quite a buzzkill.
Yeah. try to be nice though.
Okay, all right, good. All right, so here we go. Let's start with something simple. If this were a geometry class, what would we call that shape? Say it loud, say it proud. It's a cylinder, correct. But in calculus, we like to call it a disk. I don't know why. The only difference between the cylinders that you use in geometry and this disk is that the disks that we use in calculus are usually shorter and wider, whereas most of the cylinders you did in geometry were skinnier and taller. Okay, great. How'd you find the volume of that yellow thing? Let's back up. What two pieces of information would you need from me in order to find the volume of that yellow thing? The height and radius. Perfect. Okay, so let's suppose I gave you the radius, r, lowercase r by the way, and I gave you the height, h. What's the volume of that disk? Bingo. Pi r squared times h. Now, depending on how you learn this in geometry, one of the ways that I like to think about it is that disk is a bunch of circles stacked on top of each other. Each circle is pi r squared. How many circles do I have? H. Pi r squared times h, volume of the disk. Are we all good? Okay, good. Again, I don't mean to insult you, but I'm going to go slow because it'll make the stuff we're going to do later easier. Next is a washer, which is a disk with a hole punched through it. You'll notice the notation there. I'm calling the inside radius little r, represented in red, and the outside radius capital R, and then just like the disk, we have a height. How do you find the volume of that washer? Leona, go ahead.
Would you do volume equals pi r squared times h minus like little r times h squared? No. Little r squared times.
Now you're just shouting out things like R 2 pi h dog. Okay.
Yeah.
You want to
Yeah. So
take a deep breath and give us that again?
Yeah. So this is the volume of the big circle.
Uh-huh.
Which is pi big R squared times h.
Good.
And then minus the volume of the little one, which is pi small r squared times h.
Perfect. Any questions for Leo? It's basically a disk minus a disk, right? If you consider the hole in the center to be a disk of nothingness, the volume of that washer is the big disk minus the little disk. Okay, and are we good with that? This is the audience participation part of the program? Okay, thank you. All right, what we're going to do is we're going to think about those disks as being generated by revolving a rectangle. And when we're first learning about this, I'm going to make my rectangle obscenely large for our discussion purposes. Okay? This is calculus. We know that a rectangle that big is not going to work for us. We're going to shrink some things later. But I've got this rectangle. It measures W by R. And when I spin that around the x-axis, I generate that disk. So the width of the rectangle becomes the height of the, you got to look at that disk sideways, becomes the height of the disk. And the height of the rectangle becomes the radius of the disk. Okay, we okay with that? How do I take that picture and generate a washer? Liam?
You punch a hole through the middle of it. Make it.
Yes,
Yeah.
but that would be cheating. How do I do it? What do I do with that rectangle before I revolve it to get a washer?
Move it a little.
Go ahead. Doesn't matter, one of you.
Move it a little bit above the axis.
Perfect. Okay. So this we had already. You did this. Great. I chose to use W for the width of the disk because a lot of our disks will be vertical. If you want to change that W to an H, that's okay too. It's the same thing. And I'm staying with capital R here. We're going to have to make a distinction somewhere along the line between capital R and lowercase r. So for this disk, I'm just going to call it capital R. It's the only radius we need to worry about. So the, wow, you heard that right? Special time in my life. I forgot what I was gonna say. Oh, what we're gonna do today, in very simplistic terms, is the same thing we did with Riemann sums. So remember when we first started taking the area under a curve, we broke it up into rectangles. And then we added up the rectangles. And then we realized that gave us an approximation. We wanted an exact answer, so we started talking about limits. And how do I use limits to find that exact area under the curve? The same thing is true with the 3D method. Except instead of breaking things into rectangles, we're going to break them into discs or washers. And when we're done, we'll have a volume instead of an area. Okay? So, we get something like that. You'll notice, if you look carefully, that red function there, f of x, is what I want to find the volume of by spinning around the x-axis. And when I spin that, I get some weird looking shape. Doesn't matter. But I'm breaking that up into a bunch of rectangles. And this method that you're looking at is just an approximation because I've got a bunch of wasted space, just like when we did Riemann sums. So how do I get the volume more accurately? What do I change? Then,
The width of the rectangles or the amount?
say again, I'm sorry.
The width of the rectangles or the amount?
Good. Same thing, right? If I shrink the rectangles, the number of rectangles has to go up. Okay, we're eventually going to do that by taking an integral. All right, so let me stop for a second. Does everybody understand the basic idea of what we're doing here? If not, I'd be more than happy to explain it to you, but I want to make sure that we have this foundation under control before we get into examples and get into more complicated problems. We're good? Okay. Another example of what we're going to work towards. We've got that blue function. We want to find the shape of that blue weird looking thing, and we can approximate it using the gold discs, but eventually we want those gold discs to get really skinny so we get a smooth shape. And you'll also notice the word accumulate comes in there. Just like Riemann sums, just like a lot of the other stuff we did, all we have to do is find the volume of one disc, and then we use integrals to add up all those discs. All right, so we talked about this already, maximize the number of discs or change the thickness. And we want that thickness to be really, really small, so we turn that into a dx. It's the same stuff we did with areas now. Okay, now we start taking it as a calculus approach here, instead of just approximating it with big honking discs. So I've got a cool demo here, if this works. Yes. Okay, go away. All right, so here's this guy. And it was, when I did this, it was easier to do it horizontally. You don't need to know all the details. But we're going to do, most of the things we're going to do are going to spin this way, but we're also going to spin them this way. And this demo was easier to show if I did it this way. So there's my rectangle, and I'm revolving around this line. And since that line is what's called the axis of revolution, when I spin it, I get that disk that we're looking for. Okay, we've talked already about how to find the volume of that disk, and we'll do that a lot, but that gives you a visualization of what's going on. Okay, so then if I reset this, and I slide, let me clear this, display, erase traces, and then slide this bad boy over here, and erase the traces and do it again. Now all of a sudden, if we move it away from the axis of revolution, we end up with a washer. Okay. We're going to be calculating the volume of that disk. That's it. Just the volume of one disk. And then we're going to do some integrals in order to find the volume of the entire figure. Okay. Now, the good thing is we don't do shells anymore. They stopped. That's no longer part of the curriculum. But we used to have to do these kind of things too, which was not very fun. Okay?
Is that really worse?
It is actually.
Can't we do it at the same
Well, the reason, okay, so let's stop these. Stop here, stop here. The reason this is worse is because notice the rectangle is parallel to the axis of revolution. This rectangle is perpendicular. It's a lot easier when it's perpendicular. You'll have to trust me on that one.
Okay.
Okay? Okay, so then what we're going to do is we're going to take a function, and that function is going to generate our region. So this is the function, the square root of x. I broke it into 30 little disks, or I should say now I broke it into 30 rectangles. When I spin one of those rectangles, I get one of those disks I'm looking for. And based on what we know about calculus, if I can find the volume of that disk, I can integrate all the disks from A to B, and when I'm done, I have the volume. Okay, so you get all of those things added up, and you end up getting the volume of that figure when you spin it around the x-axis. Another example, and the only difference here is that I moved it up off the axis of revolution. So now it's going to be a similar shape, but it's got a hole punched through it. And you end up with something like that. And again, the good thing is you're not going to have to draw these figures. It might be a good mind exercise to try and visualize what these things look like, but it's not relevant to solving the problem. You're going to come up with a numerical answer there. Any questions before I shut this bad boy down? Okay. So how do we do that? That's the next step in the problem here. Let's start with this. I've got two lines, a parabola, and an axis. So the first thing first is I'm going to graph that so I see what I'm dealing with. And I end up with that graph over on the left. I'm looking for a bounded region. Remember, it's got to be a finite region. And the process I go through is the same over and over again. I draw a representative rectangle. I calculate the volume of the disk from that representative rectangle, and then I integrate. Okay? So here we go. It's a little hard to see, but here's my rectangle. Let's do the easy part. How wide is that rectangle? Dx, correct. We want it to be very small. And if we were doing an area problem, I would then calculate the area of that rectangle and add it up, or integrate it to add up all the rectangles. But we're not doing a rectangle. We're using the rectangle, but that rectangle is going to generate a disk. And so based on what we talked about before, the volume of that disk is pi r squared times h. If you're having trouble visualizing the disk, it's that blue thing in the right picture. Knowing that, what's h? Let's start with that easy one. Go ahead.
3.
Nope. Go.
X squared plus 3.
Nope.
Wait, which one?
H.
Oh.
Now remember, that disk is laying on its side. Here's the disk here.
Oh, H is.
Dx squared plus 3?
No?
2.
No?
dx.
Dx. Because remember, this is the height. It's sideways. Okay. What's the radius? Go.
That is x squared plus 3.
Good. That is x squared plus 3. All right, so let's stop there for a second. Is everybody good with that? Again, you have to think about the disk lying on its side. If the disk was like this, here's my H, here's my R, but now I've taken that and rotated it 90 degrees to get this blue disk. Okay. Problem so far. Beautiful. Therefore, the volume of one disk would be x squared plus 3 times dx. But I have to square this because it's pi r squared. I need a pi. And I'm going to integrate to add up all those disks from where to where. Negative 2 to 2. If this were on the non-calculator portion, I would move the pi out in front, do the integral. By multiplying it out, you'd have to multiply it out. Take the integral, plug in negative 2, plug in 2, good to go. However, for now, FN int that please and tell me what the answer is. I'm going to talk while you're FN inting. If you're going to FN int this, you could just FN int the quantity x squared plus 3 squared, and then when you get your final answer from FN int, then multiply by pi, or you could put the pi into the function. It doesn't matter. You'll get the same answer. The only thing I would caution you is that it's very common for people to forget to multiply by pi. You got to have a pi in there. And if you move the pi out in front, you can also answer in terms of pi. So I need at least one of you to not do pi in your FN int, please. What do you got, Slick? You put the pi in there. Okay, so with the pi in there, Nathan has 253.841. Did anybody do it not with the pi in there? Leona, what do you got? 80.8, just 8? Yep. 00? Okay. Pi. Good. Either one of those is acceptable. On the free response questions, they also like to throw in what are the units here. Now, I didn't give you units. So there's no units to give. You would just use units cubed. But sometimes they'll give you centimeters, inches, whatever, and they want you to make sure that you get the units correct by making it a cubic unit, because we're talking about volume. One thing I was negligent here, include an equal sign and tell me what it is you're solving for. Because when we start combining volume with area, you want to make the reader aware of the fact that you know the difference between an area problem and a volume problem. It seems trivial, but it's an important habit to get into. We're doing a volume problem, list it as V equals, and then go from there. Okay, questions. This is about as basic as it gets, and then we're going to ramp things up a little bit. You all right? I can't tell if you're anxious or scared. You're just excited to be here.
Yeah.
Love it. Okay. Anybody else? Questions? No? Okay. I don't know if I should be nervous about that or happy about my teaching skills.
We'll see soon.
Yeah, we got all that. Okay. Oh, hey, 253.841. Okay, air 5. Good. All right, now the washer method. The washer method gets more complicated because we have two different radii and we have to figure out those two different radii from the picture. But once we get the radii, the rest is pretty easy because Leona helped us with that earlier. You just got to know the big R's and the little R's. Okay. I'm going to be relying on you quite a bit. Okay, here we go. Same picture, different orientation. We got a capital R and a little r. One thing you might want to make note of, little r is the closest point for the rectangle to the axis of revolution. Big R is the farthest point. Farthest point from rectangle to axis of revolution. And then if you didn't see it, I took Leona's idea and I tweaked it a little bit to that. But again, you don't have to do it that way. You could do capital R squared pi minus little r squared pi. It's entirely up to you. That's what makes it such a great country. I find it easier to factor out the pi because I'm just going to throw it out in front of the integral anyways. Okay, how we doing? Good. Okay. Here's an example of what one looks like. You get a lampshade looking thing. Or the, what's the thing the dog wears?
Cone of shame.
Cone of shame, thank you. What was that dog's name?
Doug.
Doug the dog. Well, what was the bird's? Kevin was the bird. Kevin was a girl. Is that what we find out at the movie? At the end of the movie? Okay.
Rio.
Who cried at the beginning of that movie?
Daniel. I still cried it. Be honest.
The balloon house one from Disney. Yeah.
Up. Cried at the beginning? No? What are you, heartless? Do you have no soul? How could you not cry at the beginning of Up? Holy smokes.
You should turn it on. You should watch the scene.
No, thank you. I'm going to start blubbering right now in front of everybody. All right, another example of what happens. When we rotate a nice, cute little triangle floating above the x-axis, we get these pretty shapes. Now all of a sudden we want to find these weird things. Okay? But again, our goal is to find the volume, that's it. You know, we don't have to draw the pictures. One of the interesting things about this is that it's a fairly common production method when you're making different things. I mean, there's items in the world that are made using this method. We don't need to see that again. I think we're good. Well, let's see what happens. Hold on. Hold, please. I think it's the same. Yeah, we did this already. So we're
Do
good.
it again.
No, we don't need to do it again. You be quiet, mister. Okay, so we got that. And you know that's got to be important because it's in an orange rectangle. A lot of parentheses going on in there. A lot of brackets. A little craziness, but you get the idea. It's always big, mine is small. Maya, lose the hood. Thanks. Are you cold?
What?
Are you cold?
No.
Are you in a gang? All right, good. All right, ready for some fun? Oh, there's another example. All right, well, we'll do the whole thing. We're gonna do Doug's cone of shame without a hole in it, so it'd be more like a, I don't know, a hat, a bowl, funky bowl because it's got some weird stuff in the middle, but it's still a bowl. What's that?
Maybe we'll make a better hat. Or
Probably.
something.
Yeah.
Bowl of shame.
The bowl of shame, I like that. Okay, so I've got this cat's eye looking thing, and we've seen that before. It's the bounded region between the graph of the square root of x versus x squared. It meets at 1, 1. Again, we've seen this before. So I drew my representative rectangle, and again, I'm doing the representative rectangles very large because we're just learning. Okay? When I spin that puppy, I end up getting a disc. And I shouldn't say a disc, I'm sorry. I get a washer. Let's see if I can do this. The sound effects help. Wow, that's horrible. Let's pretend that didn't happen.
If you squint, it looks good.
Yeah, great. If you close your eyes, it looks fantastic. All right. So what I need to know is capital R and lowercase r. And in this picture, I labeled that already. If I didn't have the labeling in there, it would go something like this. I know that that is the farthest distance away from the axis of revolution, so this becomes capital R, which is labeled there. This is the closest point that that rectangle hits the axis of revolution, so that becomes lower r. Lowercase r, I should say. And then the functions come from the functions themselves. So the higher limit is hitting the function square root of x. the bottom function is hitting the function x squared. And then delta x, again, big fat rectangle, but I'm not going to use a big fat rectangle. I'm going to let that shrink down to really tiny, so that becomes dx. Hopefully I didn't give it to you, but what I would like you to do is then write the function or write the equation that you would use to find the volume of the bowl of shame, based on that information that I just worked through with you. Set up your equation, and then just to save time, fn int that bad boy and get a number. In this particular case, you'd have to solve it. I agree, skip that because we've done it before at 0 to 1. So yes, that is correct. But normally in a problem like that, they expect you to set the functions equal and start with. I'm going to talk while you're working. Kush just asked a great question. What are the regions here that we're going? Where are we taking washers to and from, or from and to, whatever? The reason I didn't do this is because number one, they're in the picture, and number two, we've worked with this shape before. The shape has points of intersection at 0 and 1, so those should be your limits of integration. Because we're going to take washers from starting at 0 all the way up to 1. I would take some answer suggestions.
Well, I started off with v equals pi.
No, I don't want that. I just want the number first, then we'll do the
The
function.
number. You mean like?
The answer to the question. What's the volume?
Oh, wait, I haven't. Sorry.
Anybody else?
I think it's wrong, but I got 0.942.
Way to start with I think it's wrong, so you feel safe if you're wrong, and
Yeah.
everybody will still respect you because you knew you had it. Just give me the number.
0.942.
0.942? 0.942. Jessica, yes? Anybody else? All right, so we're going to go with it. What's your function look like? So I did that. You saw that in the picture. I know the outer radius. I know the inner radius. And then you got two choices. Do you either just go memorize the formula and plug and chug, or do you understand what you're doing? Either one is okay. I just don't like to memorize. So I realized that in order to find the volume of that washer, I need to take the big radius and square it times pi, take the little radius and square it times pi, and then subtract the two. So I end up with that puppy. And like I mentioned before, I like to move the pi out in front so it just stays out of my way the whole time. That would be a great problem to see on a non-calculator portion because those numbers are easy to work with. Obviously, the square root of x squared is just x. You all know that that x squared is x to the fourth, and you know how to integrate each of those. And you're plugging in nice pretty numbers like 1 and 0. When you do that, you get 3 pi over 10. Please tell me that's 0.9 something or another.
Yeah.
I do, oh, good. So I did it right also. Okay, good. We're on the same page. That's 2 of the 4 things we need to worry about. How are we doing? Okay, good. What if we spin it around different axes? When we were doing area, one of the things I tried to burn into your brain is top minus bottom, right minus left. That's going to become relevant to what we're doing here too. Always, always, without exceptions. It's top minus bottom, right minus left. If you do a good sketch, if you draw a good representative rectangle, these problems can be made a lot easier. Okay, so I got this guy. And I got some information about it. For those of you that aren't quite following what's going on, let's color code this bad boy. That's the red guy. The light blue is this guy. And the dark blue is this guy and this guy. So now I'm going to revolve it around a different line. But just to make sure we're on the same page, let's do a couple things first. Let's forget about this for a second. And let's spin this puppy around the x-axis. Okay, so when I'm doing a problem like this, when I draw my picture, that's how I show in my picture what I'm revolving around. We good so far? So you don't have to write this down, just watch. I'm going to do this just like the problem we finished up, but now we have different values. I look at this and I say to myself, excuse me, where's the farthest distance from the axis of revolution? That would be here. So this becomes capital R, which is the red function. Then I look at this and I say, well, where's the closest spot? It's there. That becomes little r, which is the light blue function. Okay. Then I plug and chug. Okay. The integral of, put the pi out in front, capital R squared is x squared plus 2 quantity squared minus little r squared, 1/2 x plus 1 quantity squared dx. And I'm going to take it from 0 to 2. Oh, sorry, I lied. 0 to 1, because that's where this guy is. Okay. And whether you multiply that out or you fn int it, we're good to go. All right, any problems? Okay, let's get rid of this now and do it what it originally asked for. Erasing, erasing. Okay. Now, we're going to revolve around the line y equals 3. So not only are we not doing it around the x-axis, we're going to do it around an axis that's above the figure. Okay. So here's my line at y equals 3. The process I just went through to revolve it around the x-axis is the exact process I'm going to go through to revolve it around this yellow line. I'm still going to figure out where the farthest point is. I'm going to call that R, capital R. I'm going to find where the closest point is. I'm going to call that little r. And I know I'm going to get a washer. How do I know I'm going to get a washer? Because my rectangle is not touching the axis of revolution. We'll go through that later. Okay. This point right here is the farthest point away from the axis of revolution. So this is capital R. This is the closest point. Little r. So now I do some top minus bottom. What do I mean by that? That means that if I look at this distance r, capital R I should say, how do I get the distance capital R? I go from the top, which is 3, down to the bottom, which is the function. 3 minus parentheses. The bottom is the line, 1/2 x plus 1. And that whole thing is squared. So let me stop for a second to make sure you understand how I got capital R. Are we good with that? Don't overthink it. Remember, top minus bottom. What's the top? The yellow line, which is y equals 3. 3 minus the bottom, which is the blue line, 1/2 x plus 1. Be careful with parentheses. Minus. Bracket. Little r. Top is 3. Bottom is the parabola. 3 minus parentheses x squared plus 2. Close parentheses. Square that whole thing. Add them all up. Don't forget my pi. And I'm taking them from 0 to 1. Okay. And I'm done. Probably, oh, wait, sloppy. dx and volume. That's better. A doable problem by hand, well, we don't really want to do it by hand because that's not what this is about. We're not practicing taking antiderivatives. We're practicing how to come up with these values. Any questions? Or are you so confused you don't even know what question to ask? I love these chats we have all the time. That's what I look forward to every other day. Let's move on. I think that's what I have there. Yep. Okay. Top minus bottom for capital R. Top minus bottom for little r. Life is good. What happens when it's not around the x-axis or it's not around a vertical line but a horizontal line? It's the exact same thing. It's just y's instead of x's. Either on your calculator or on Desmos, graph that problem, please. Y equals x to the fifth from 1 to 32. You're going to have to pinch. I would probably do it on Desmos because it'll be easier to pinch than change your window settings on the calculator. Just so you get an idea of what's going on. I don't remember if I have a picture on this.
No, the other side. Okay, never mind. So I didn't give you a picture.
Okay, we good? That's what I want to revolve around the y-axis. So I'm going to put my little rotation symbol up here. Just like when we worked with area, if my representative rectangle is horizontal, everything shifts to y's. My representative rectangle is going to go here. It can actually be anywhere in that region. It doesn't matter. I just happen to draw it there. One of the things that's going to happen when you're doing these problems is you're going to get confused. Is that a disk or is that a washer? There's a simple rule to solve that problem. Does any representative rectangle always touch the axis of revolution? If the answer is yes, then you have disks. If there's any point where anywhere that you could draw that representative rectangle is not touching the axis of revolution, then you're going to switch to washers. Okay, so notice whether I drew my rectangle there, or down here, or up here, or anywhere in between, it's going to be touching the y-axis. So I know I'm going to be working with disks here, which is good because I only need one radius. How long is that? Go.
Y's to the field? No. Just next to it.
Gotta be in terms of y.
Y to the, how do you even say it, the root 5?
The fifth root.
Yeah.
Yeah. Okay. That's it?
Yeah. Yeah, sorry.
Okay, so Liam's not wrong, but I'm going to give you an alternative way to think about it. I'm still going to focus on right minus left, especially when I'm starting the problem. So the right is the function that Liam already helped me get, which is a fifth root of y, minus the left. Well, the left is 0. So early on, I'm still going to write it this way. As you get more comfortable with this process, or pretty early on, you're going to realize, I don't need that minus 0 in there anymore. It's a waste of time. But while you're learning the top minus bottom and the right minus left, you might want to stay with it. My limits of integration. My first rectangle could have been all the way down here at 1, and the highest I could go with it would be 32. So that would tell me my limits of integration. I'm finding a volume, and my differential is dy because I'm working in terms of y. Questions about that setup? Excellent. Fn int it. Give me a number. Question or answer?
Question.
Yeah.
If we were to use it in terms of x, would that be like what you were talking about earlier with the thing that we're not
shells.
choosing one?
Yep.
Shells? Okay. That makes sense. Okay.
It has to do with the orientation of the rectangle.
Right.
Yeah.
Oh, 90.714.
90.714. Is that with or without the pi? Did you want? With pi. Okay, somebody confirm. That's without pi. So,
Oh, wait,
Allie, what's
without.
that times pi?
284.97.
Beautiful. Give it to me again. 284?
Yeah.
284.987 or 897?
987.
987. Okay, beautiful. Any problems with that one? All right, real quick, let's talk about if you didn't have a calculator for that bad boy. The 0 would disappear. What's the 5th root of y squared? Who's talking? Is that you?
It's just 2 fifths.
Yeah. This would become the integral from 1 to 32 of y to the 2/5 dy, and don't forget the pi out in front. Okay. And again, you could take it from there and plug in the numbers, and it wouldn't be fun to put 32 in there, but notice that 32, there's a reason why I chose 32. Why is 32 significant here with that number? Okay.
Because you can do the 5th root of it.
Good. 5th root of 32 is 2. So it makes the numbers a little bit easier when you start plugging each other. But again, I don't care about solving the antiderivatives today. I just want you to get comfortable with the concept of what we're doing. Okay? Problems? Questions? Oh, by the way, before we move on, let's suppose in the lovely color of blue, let's suppose I spun this, instead of around the y-axis, I spun it around the x-axis. Would I get discs or washers? Washers, right, because it wouldn't be touching the axis of revolution. And to make matters worse, you'd have to do 2 different problems. I'd have one there, and then I'd have another one over here. And that's why we didn't do it that way. But yes, we would get washers because not every rectangle is touching the axis of revolution. Did that? Yep. Oh, 284 point. I got the same thing. Beautiful. Okay, that's just a summary of what we've done in calculus speak. So we're good to go. That's the disk method. Washer method we talked about. Playing off of this idea with the blue rectangles, I have this example just to talk about a little bit, and that is, what if I'm taking that parabola and rotating it around the y-axis? You have to use 2 different integrals. And if you're smart about it, you don't have to do 2 different integrals because you can all find the volume of that bottom thing. By bottom thing, I mean this guy over here. from this point down, that is just a cylinder. So just find the volume of the cylinder. Okay, and then use the calculus for the upper part. Good? Okay. Yeah, blah, blah, blah. Okay, scariness, we're good. Top minus bottom, et cetera, et cetera. And a final answer of 3 pi over 2. And again, I didn't necessarily want to go through this problem piece by piece, but I wanted you to understand that you can be crafty about it and use some of your geometry knowledge to save yourself some hassles and not have to do calculus by finding the volume of that cylinder at the bottom. Click, 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 click. Yeah, okay, good. And we're done. Anybody? Do you know who that is? Well, then you wouldn't get the joke. What's the white thing?
A washer.
It's a washer. What? Do you know what that black thing is?
A floppy disk?
It's a disc. Do you know who that is?
Dishwasher.
No. It's Method Man.
Oh, yeah. That makes sense.
Washer and disc method, man. You know how much time I spent on that? A good 30 seconds.
You know when you did that?
When I did it?
Yeah.
A couple weeks ago?
I think maybe a couple weeks.
Yeah. Well, if I said a couple weeks ago, I had to do it from scratch. A couple weeks ago.
I thought it was a joke.
Oh, the joke.
I thought it was the best thing.
I mean, I understand you guys don't know who Method Man is. He's an old school. Okay, so hold on. You don't know who Method Man is, right?
No.
How about, let me fire off some names. How about Ice-T?
Yeah.
Now, do you know Ice-T from his rapping or from his SVU stuff?
SVU.
How about Ice Cube?
Yeah.
Yeah, from what? From where? His rap? Okay. Well, you know Snoop Dogg.
Yeah.
I'm trying to think some of the other old school rappers. Flavor Flav? No, he was just at the Grammys this year. He's the guy that wears a giant watch or clock on his necklace. One of the founding members of Public Enemy. Wow. Yeah, I know.
We talked about the Beastie Boys and religions.
Oh, very nice. Cube was a big Beastie Boys fan.
We talked about him and then Buddha with that.
I'm sorry, did you just use the Beastie Boys and Buddha in the same sentence?
It was really cool.
That does
Like,
not seem.
It's because one of the lead guys like ended up converting to like Tibetan Buddhism, and
What?
and it was like and then we compared his life to the life of the original Buddha. It was really cool.
I can't think of anyone.
Talk to him about it. He'd probably explain it to you. One of the, I remember it really well.
Excellent. Okay. Man, what's better?
Ask.
I don't even know.
Yeah, sure. Come on, let me stop this.